Hello, I'm Ezra. This is AP Calculus AB and BC Review, Unit 8, Applications of Integrals. In this unit, we talk about average value of a function over some sort of interval. We have the area between curves. We look at disk and washer method, as well as cross-sectional area to figure out how to find volume of certain shapes. And then for our BC only topic, we look at the arc length of a function. So let's begin. Average value. So what is the average value of a function that looks like this? If this is the value 3, the average value of this function from, let's just say, some arbitrary 0 to 4, it's going to be 3. Surprisingly. And that's because the only value is 3. So, what about a function like this that oscillates around this number 2 between 0 and 5? Well, you might be able to guess. The average value is going to be 2. Now, what about for a shape that does not look so regular? What about for this? Over this interval, 0 to b, what is the average value, the average f of x that this function has? Well, you're not going to be able to just draw a line and figure it out. Maybe something like here. But no, maybe it's a little bit higher because we have these peaks over here. You're not going to be able to figure out just by doing this. So, there is a formula, of course. And it is a pretty easy formula at that. So, the average value of a function on an interval a to b is just the integral of the function from a to b times 1 over b minus a. So, if the difference in b minus a is 3, let's say you're integrating from 0 to 3, you want to find the average value of f of x from 0 to 3. You're just going to integrate f of x from 0 to 3, and then times it by 1/3. So, let's take some function, x squared. Our nice function x squared. If I said, what's the average value between 0 and 3? What's the average value of x squared on this interval? So first, let's write out our formula. 1 over 3 minus 0, so I'm just going to write 3. And then dx. Alright, so it's integrating it now. I mean, 1/3, we're going to keep that on separate. Then we're going to have x cubed over 3. Okay. And this all goes from 3 to 0. So the 0, when you plug it in, is going to give you a 0 solution. So that doesn't matter. We can only focus on this 3. And this equals 1/3, 3 cubed over 3. So this ends up being 1/3 times 3 squared, because 3 cubed over 3 is 3 squared, which ends up being 3. So, the average value of x squared between 0 and 3 is 3. That is it. That is our answer. If you are given like a table or something with arbitrary values, and we're going to say between times 0 to 4, or 1 to 4 here, and you get 6, 9, 10, 5, then you will have to, for instance, do a Riemann sum to figure out what the approximation of the integral is over here from 1 to 4. This would be an FRQ problem. So you do an integral from 1 to 4 of your f of x function, and Then you just divide it by 3 because your interval is 1 to 4. So 1 over 4 minus 1 equals 1 over 3. So if I said I wanted to find the average value of this function y over the interval 1 to 4, I would just take our quote-unquote integral, which is really an approximation of a Riemann sum, and then divide it by 3. One last thing that you might see regarding average value on the test is it will tell you the average value of f of x, I'm just going to denote it as f average, between 0 and 5 is 30, just 30. And then it will say the average value of f of x between 5 and 7 is 18. And then find the total area under the curve between 0 and 7 of f of x dx. So some sort of relationship like this, where you are given the average or you're given some sort of integral, and then it wants you to find a total integral. All right, how do we do this? Well, let's just translate these into function forms. So the average value between 0 and 5 is 30. Cool. What does that mean? That means 1/5 times the integral of 0 to 5 f of x is 30. Okay, the average value between 5 and 7 is 18. Let's translate this now. So that means 1/2 integral from 5 to 7 f of x dx equals 18. All right, now we only really have 1.5-ish more steps. To find the integral from 5 to 7 and from 0 to 5, all we have to do is multiply this over. So, given that the average value between 0 and 5 of f of x is 30, then we can conclude that just the integral from 0 to 5 of f of x is 150. Because I multiply both sides by 5 to get rid of that average, and then I end up with this relationship. Same thing over here. I'm going to multiply both sides by 2 to get rid of this average relationship, and then I can conclude that the integral from 5 to 7 of f of x is 36. Now, to find the integral from 0 to 7 of f of x, well, now we just add these together. We get 186, and that will be our answer. So, there will usually be one average value question on the BC test and AB, and it is important to know that you can convert an average value expression into an area under the curve expression, and vice versa, by just, taking your area under the curve, dividing it by the interval. So that is average value. Now we're going to look at, very briefly, area between two curves, because this is quite easy and quite intuitive. So if I take a curve right here, and then I give you a straight line. Okay, if I wanted, let's mark some arbitrary x value here. If I wanted to find this area, then what you have to do is take this area over here, which is just the integral of this function over this interval, right? And then subtract this area from it, which is just the integral of this function on that same interval. It makes sense because if you have all this area and then you take away just the area under this, you're left with just the area above this curve but below this curve. So how would that look? Well, let's just take the functions sine of x, and then we're going to have x squared. So sine of x is actually bigger than x squared between 0 and whatever value this is. It's around 0.8. So if you wanted to find this area between the two curves, I'm going to say that this x value is a. Here, you would just integrate from 0 to a sine of x minus x squared dx. Because integrals agree with addition and subtraction, you can just keep these in the same integral. There's no need to move it out. You can if you want to, if you feel the need, but keeping them in the same integral will net you the same result. So, just to reiterate, if you have some sort of function above another function, and you want to find the area between the two functions, you just take the area of the top one subtracted by the area of the bottom one on whatever interval you want to find. Alright, now we're going to look at some of the less intuitive stuff. So, this is called the disk method, which is rotating a function around the x-axis. So we're looking 3D now. So if I were to give you a function here, I'm going to give square root of x because it's pretty nice to work with, and told you, okay, what if we rotated this around the x-axis and then we made this sort of like cone shape? What would be the volume of that shape? Well, there is a formula for this, of course. So the formula is pi integral a to b r squared dx. So what is this r? This r is the radius of these imaginary circles that we're taking. So how would you find the volume of a shape that's rotated? Well, when you rotate the shape, like I drew out here, it's essentially going to make one big circle cross-section, as you can see here. And this repeats infinitely until the very back of the function, where it gets nice and small, and then the function ends over here at x equals 0. So what you're essentially doing is, instead of integrating the area under the function, you're integrating all these little circles that go smaller and smaller, infinitely small. And the radius of these circles is just the function. Because you have half of the diameter of this new shape is the function, because it's rotated 360 degrees around. So your r in this case would just be the function. So if I wanted to rotate this square root of x function between 0 and 4, alright, I can take pi times the integral from 0 to 4 of my radius function squared dx, which is the same thing as taking this, because the square and the square root cancel out, and then you end up getting pi x squared over 2 between 0 and 4, which ends up giving you 8 pi. So, what this is saying is that the volume, if you rotate square root of x between 0 and x equals 4, so this area right here, if you rotate this function around the x-axis and find the volume of that shape, it's going to be 8 pi. So let's look at another example of this. If we take the function y equals x, and we wanted to rotate it about x equals 3, well, what is that going to look like? Well, it's going to look, again, like a rotation, kind of like this, like a big circle, and then it gets smaller and smaller. So over here, it's going to end up being pretty small. So, let's plug it into a formula. Pi square root from 0 to 3 of our radius, which again is going to be x, because this is our diameter. I'm going to mark it in red. This is our radius, and then the other side of this imaginary like rotation, the imaginary circles that we're talking about, is another r. This is our diameter. So our radius is just going to be the function. So our r squared dx. So now pi integral 0 to 3 x squared dx. Pi square root 0 x cubed over 3 between 0 and 3, and that's going to end up giving 9 pi. So when you take the function y equals x, rotate it around the x-axis, you can think about the rotation like, imagine taking a line and doing like a circle around some sort of line, like with your hand. You can see it kind of makes a circle. That's essentially what we're doing here. That volume will be 9 pi. Now, there's another way we could have done this. In fact, if you have like a linear function like this, and then you take the volume of this, this is a cone. So the volume of a cone is 1/3 pi r squared h. So r is going to be our function here. So, and our h is going to be the x value. So our x value is 3. Our y value is 3. So 1/3 pi 3 squared times 3 is going to end up being 9 pi, which should match up with our answer over here, and it does. So if you wanted to find it by using this formula, then you also could have done that. Now I'm going to do one more final example. Take the function x squared, and I want to rotate it around x equals 1. I'm going to draw my little rotations. Okay. Again, pi. Do not forget your pi. And do not forget your squared. Those are the two things that graders are looking for when you're doing the disk method. So, now we have pi integral 0 to 1 x to the 4th dx, pi x to the 5th over 5 from 1 to 0, and then you get pi over 5 as your answer. So, what would happen if you had an area you were rotating, which was not just some area under the curve, like this, that was being rotated around? What if you had something a little bit more unorthodox, like the area between two curves? So, we're going to have y equals x, and then y equals x squared right here. Intersection point right here at x equals 1, y equals 1, and then we're going to call this radius r. So now what we're saying is, what happens if you took r and rotated it around the x-axis? Well, the formula does not seem to be able to work here because we don't have the area under. So now we're going to have to use something called the washer method, which is essentially having a hole inside of your disk method function. So what it says is that if you have two functions that create an area, such as this right here, r, and then when you rotate it, there's going to be all this empty space under here once you rotate it. However, if you just did the integral way, it's going to not think of that as empty space, but actually think of it as filled in space. So what you have to do is have to do essentially two disk methods and subtract one from the other. So you have integral from 0 to 1. And then what you have to do is you have to take your first disk method and subtract it from your second disk method. So what this is giving is the volume of this shape when rotated about the x-axis. That's it. It doesn't look that much crazier. You have to just think about it as, okay, this function is further from the x-axis, right? This one is on top of the x squared function. So when I rotate this, it's going to fill in all of this area under here, just like we showed in the previous one, where it would fill in this area like a circle. Okay. And then this one, we need to subtract this area rotated around so that this bigger top function, its excess area under here gets removed, if that makes sense. So we have our top function, disk method, minus our lower function, disk method. And I'm not going to bother to do the integral right now, but this is your answer for this. Now, I'm going to do another one where it is negative x squared plus 4. So we're going to do here. And then we have x plus 2. So here. Now, this is our area. Really weird one. These two guys meet at 1, 3. Okay. So, the way we go about doing this around the x-axis is the exact same. Pi integral from 0 to 1 top function, which is our negative x squared plus 4. We're going to do negative x squared plus 4 squared minus our bottom function, which is x plus 2. And then squared that. So again, we have our disk method here, which is the top disk method, minus our disk method here, which is the bottom disk method. And this would give our answer for this area R rotated about the x-axis. So what happens if it's rotated about the y-axis? Well, let's say you have function square root of x, but instead of rotating it this way, it actually wants you to rotate it this way. Well, all you have to do is set a y function in terms of x instead of an x function in terms of y. Or other way around. Normally we have y equals something, something, something x. To find a x function in terms of y, you basically just isolate x. So in this case, x equals y squared. This is your y function. So now we're going to integrate this, and then you find your y value that it belongs to. So if this is x equals 4, y equals 2, instead of integrating from like 0 to 4 on this x squared function, you're going to integrate from 0 to 2, and then you have your y squared dy, that is an x, y squared dy, and then square your function, because this is your radius. So it is the same principle, except now you just you find an x function in terms of y, and then use dy. And this will net you the correct answer for rotation about the y-axis. So now, if I go to a washer method, like what I did here with the x and then the x squared. Okay. Now what would happen if instead of rotating this about this x-axis right here, I instead were to rotate it about the line y equals 2, how would I rotate this shape about a line that's not on the graph, not anywhere close to x? How would you do that? Well, essentially, you have to set this and this with respect to each other so that this is essentially acting like it's on an axis. So what do I mean by that? Basically, you're going to take this whole area and move it up to so that the area is placed up here. So now the bottom of the area is going to be at y equals 2, and then when you do the formula, it's going to act like this y equals 2 line is the x-axis, and it will give you the correct answer. So, what do I mean by that? Well, let's first set up what we're going to do between 0 and 1. Now, how would you do this? Well, your x line is going to be x line, and then you add 2 to get up here. So, you're going to have x plus, or what's it called? Minus 2. So why minus? Because you are going to be putting this top onto the bottom. So it looks like this, but in reality, this is just going to give you more area. So conceptually, you're thinking about it like it's on top of the y value, but in reality, you're moving this to below it. You're moving it down to, so that when you do the values, it's just going to rotate about x instead of coming up here and rotating it about x. So you have your x minus 2 squared, and then again subtract x squared minus 2 squared dx. Okay. And now this would be your answer. Rotating this area about y equals 2, you're going to get this function, or this expression, I should say. Now, what if you did something like just the function x about something all the way up here, y equals 3. This should be easier to visualize. Now, if you were to rotate this about here, then you would have so much excess area. So in theory, you could do the washer method over here. So you could have your rotated function and then do the washer method, but that is just going to be more tedious. So we're just going to do pi integral 0 to 3 of x minus 3 squared dx. This is our disk, and we just moved it down 3. So your x is now here, and then now you can do your circles. Okay. Finally, for area, we're going to talk about cross-sectional area. So, what this is saying is, if you have a function like this, on each point of the function, there's going to be some sort of shape sticking out of the paper, sticking out of the screen. So, for instance, if it was a square sticking out of the screen, you would have one square line here, and then a square that was sticking out of the screen, and then another square, and then another square line that was sticking out of the screen. So this area would be r squared, because you have this r, which is like the height of the function, and you have this r because it's a square, so r times r. So you have this across the entire function. And even over here. Okay, so let's see how you would do that. So if I take the function negative x squared plus 1, alright, And I said that for every single x value between 0 and 1, there was a square perpendicular to the x-axis. I'm using the language that they use on the test. There's a square perpendicular to the x-axis for every single x value, where the radius of the square, or the side length of the square, is the function length. You're essentially integrating from 0 to 1 an area function, and you have to be careful here, because there is no pi. This is the first time we're not using pi in these integrals in this unit for these areas. So there's no pi here. You're just integrating the quote-unquote area function, which in this case, if it's a square, it is r squared dx. Okay, what is r? Well, like I just said before, r of the square is the height of the function. So, the r here is negative x squared plus 1. So, 0 to 1, negative x squared plus 1 squared dx. This is our answer. This is called cross-sectional area. So it says for each cross-section, there is some sort of shape perpendicular to the x-axis. And that is the area, if these are all squares. Now, if I take a different shape, such as, we're going to combine basically all of this stuff we've been doing. So if I have square root of x, again, classic function, and then I have here, this is going to be x over 3, square root of x, and this point is 9, 3. Alright. Here's my area R. For each cross-section perpendicular to the x-axis, there is a semicircle with radius 1/2 the distance between the functions across the area R. So, you might be tempted to integrate from 0 to 9 and then say, okay, well, square root of x minus x over 3 is my radius. So this squared, and remember, 1/2 pi r squared is the formula for semicircle. So let's just put our pi over 2 on the outside. Is this right? No. This might get you half credit, but this is not correct because this is not technically our radius. So let's take a step back. I'll leave that there. Our radius is only going to be half because this whole thing will be the diameter of our semicircles. So, the actual radius is 1/2 of this function minus this function. And that needs to go inside the square. So, 1/2 square root x minus x over 3 squared dx, and then you can have your pi over 2 on the outside. And then this will be your answer. So remember, you have to take the value between these two, not the entire value, and square it. That's your radius for a semicircle. Because radius for a semicircle and like r for a square are going to be different. Alright, so that is all the AB topics. There's guaranteed one FRQ on the AB test of those topics. So disc and washer method, area between two curves, rotating about a line, and then cross-sectional area. Now, our only BC topic in this unit, and it's quite an easy one, is arc length. So, basically, it just follows a formula. The arc length from a to b of a function is just the integral of square root 1 plus f prime of x squared. So, what does this mean? Well, if you take the function x squared, for example, right? And you wanted to find the arc length of x squared. So basically, the distance of x squared between 0 and 3. So, like, how long is the line between 0 and 3? Let me trace this line. How long is this line? What's the length of it? Well, just plug it into the formula. It is really that simple. Square root 1 plus, okay, what is f prime of x? F prime of x, if f of x is x squared, f prime of x is 2x. Square it dx. So, the arc length is just going to be 1 plus 4x squared, all under the square root, dx. This is your answer for arc length. So, this very often will be on an MCQ. On the BC test, you automatically have one arc length question. So, there's a few ways it can be asked to you. One way is like this. Which expression represents the arc length of x squared from 0 to 3? It's going to be this. Another might be to ask you for the arc length, in which case you would just plug this in onto your calculator and then find whatever decimal place it is. If it's, I don't know, I'm just going to put some random 3.489, who knows. You would need to find that. Those are really the main two ways that the question might be asked on the AP test. So this is a very, very easy topic as long as you remember the formula. A to b square root 1 plus f prime of x squared dx. So remember, f prime of x squared. So do not mess that up. You take the derivative first. So if you have x squared, you take the derivative first and then square the whole thing. And remember that square root. So, to review, or to recap, for this unit, you need to know average value. There is always going to be an average value question in some shape or form on both A, B, and BC. These are free points. Average value is so easy. It is quite literally integrating. If you know what an integral is, you should be able to get these average value questions correct. It's just 1 over b minus a, integral from a to b. Okay. Then remember your volume methods. Review the video again to find your volume methods, because there's a few. There's disk, washer, and we went over cross-section. So these are the ones that are going to be tested on the AP. And then, area between curves, you should remember, but that should come intuitively over time. And then finally, if you're BC, memorize. Yes, memorize. I know that word is not usually good, but in this case, memorize. You just need to memorize that formula, and you will pretty much always get the arc length question correct if you memorize that formula and know how to use it. That was Unit 8, Applications of Integrals. Thanks for watching.